This is the 3-2 notes for Calculus 1. In the prior section, you learned about the derivative definition and how to apply it. So I did bring up a word in that section. It was the word differentiability. So differentiability is essentially the ability to take a derivative of a function. So if it's differentiable, a derivative can be found. If it's not differentiable, it cannot be found. So yes, there are some functions that you cannot find a derivative for, and this is important, and we're going to talk about the lack of differentiability in this section. So how do we start out? Well, we're going to be talking about the relationships between specifically differentiability and continuity right here, so that we can actually make some of these conclusions. So a very common popular theorem, very simple, is if a function is, so f means a function, if a function is differentiable at some value a, then f is continuous at a. Okay, so if we know that at some point on a function that it's differentiable there, then we know it's going to be continuous there. This in itself is a solid theorem, but it doesn't really help us with determination, mainly because we're trying to prove differentiability from continuity most of the time, because continuity is really easy to see. So what we do is a different version of that formula. In logic speak, it's called the contrapositive. You don't need to know that, but it's called the contrapositive. Basically, it states, if f, the function, is not continuous at some point a, then the function is not differentiable at that point. So what they did basically is, to take the contrapositive, you have to take the hypothesis and the conclusion, switch them, and negate them. So by negate, I mean use the word not. So again, you don't need to know that, but that's where the formula comes from. So basically, in order to prove that something is not differentiable, all we have to prove is that it's not continuous at that point. So there are various scenarios that we will run into where you will be like, oh, it's not continuous, so therefore there's no way I could take a derivative at that specific value. Now, one small thing before we get started with that. One of the concepts is when I say it's not differentiable, so if I have some graph, right, and I take a point, remember a derivative is a slope of the tangent, a tangent line. So if I can find the slope of a tangent line, let's say if I drew a tangent line here, that would mean that this is definitely going to be a derivative at that point, or differentiable. Just like if I went anywhere else on this curve right here and I drew a tangent line, because I can find that slope, it means it's differentiable. So there are times, though, when you cannot do that. So that's where we're going to actually start right here. It says here 4 different instances where functions are not differentiable at a point. So what I'm going to do is I'm going to go through all these scenarios and I'm going to talk about why they're not differentiable. Your goal is to sort of remember them by the key words that I provide. Okay, so let's look at these different scenarios that develop on a graph, and I want to be very clear about this. When you look at this graph, this is the graph of the absolute value of x, which most students remember as the v graph. So the key is that it's not that this graph itself is not differentiable. It's that it's not differentiable at a point. Okay, specific point on here, it's not differentiable. And we use this word to help us remember where. It's at the corner, which is at x equals 0. Okay, so just to be clear on what that is. So if I were to, let's say, make a point over here, and I was to draw, let's say, the slope of secant/tangent lines as we approach here, basically I can find the tangent line, the slope of that tangent line. Just like if I was over here and I drew a tangent line, I can find that slope physically. And it's a very legit tangent line. So therefore, there's a derivative that exists at that point, and it's therefore differentiable. So here's the deal, though. If you go down and find all of these slopes, right? If you kept on finding slopes as they approach here, as they go down, they are going to be at different values. So we could make sort of an argument that the slope of this line is, let's say, 1, and the slope of this line is, let's say, -1. So you can see that as we approach here, the slopes are going to converge at x equals 0 at different values. The slopes are different values. Whenever that occurs, that means that when you reach that point, the graph is not going to be differentiable at that point. So another way to think about it is, it's very easy to draw tangent lines and secant lines and all that good stuff out here, but how do you draw a tangent line here? Like, where do you draw it? Like, who knows, right? So if you can't draw a tangent line in these scenarios, then you can't find the derivative at that function, because you need the slope of the line you're going to draw. So therefore, it's not differentiable at that point. So anytime you see a corner on a graph, you know that it's not differentiable at that point. Okay, so what about the next scenario? So what do we got? So if you look at this guy right here, we have what's called a vertical tangent. Okay, we use the graph of the cube root of x in order to show that. Note that this is the same as this, if you remember from algebra. X to the 1/3 is the same as the cube root of x. This is something, by the way, that you will absolutely have to remember for this class, fractional exponents. But going back to the actual graph. The graph is funky. It's sort of a sideways graph that goes through. It's sort of like the cube graph, but turned sideways. So what is that? What's the scenario here? So again, the same idea. So let's say we drew like a point here and drew a tangent, right? Clearly we know that we can find that slope just because it's a line, right? So if I drew one like here, right, and I drew a tangent, that's looking pretty good. I could find that slope. But what if, for example, I went in a different direction? So let's say I went to, again, x equals 0, and I tried to draw a tangent. What would that look like? Well, the tangent line looks like a legitimate line, but the tangent line is actually vertical. So hence, vertical tangent. So you might say, well, what's wrong with that? Can't we find the slope of that? And the key to understanding this is, no, you can't. You can find the slope of a rising line at some positive number. You can find the slope of a diving line at some negative number. You can even find the slope of a, I drew that wrong. A little bit clear. Of a horizontal line. The slope of a horizontal line is 0. But what do we know about the slope of vertical lines? It's actually undefined. N is undefined. So therefore, if we can't find the slope of this line, then it can't be differentiable at that point. So therefore, slope doesn't exist. Therefore, slope of tangent line doesn't exist. Therefore, not differentiable. Okay, so what's next? Okay, so this is the graph of x to the 2/3, okay? So x to the 2/3 creates this. So if I was to draw like a seagull, because I'm a terrible artist, I probably would draw it like that. So this is actually the graph of a seagull of that I would draw. So what does that look like? It's called the cusp. So a cusp is essentially a corner, but sort of curved. It's also sort of a cross between a vertical tangent too, but you don't really have to know that. I tend to be very flexible with interchanging the terms corner and cusp. But it's good to know both of them so that you get an idea of what's going on. You can clearly see that it has the same exact logic as the corner. So what's going on? So as you're approaching, this value at x equals 0, where are you going to draw the tangent line? I don't know. Where are you going to draw it? Who knows? So in this scenario, basically because you don't know where the tangent would go, you would clarify this as being not differentiable at the point 0, when in reality you could draw tangents anywhere else and it's fine in other locations. It's just not differentiable there. Our last scenario is just a simple concept, right? And it comes straight from the definition on the front page. If f is not continuous at a, then it's not differentiable at a. So going back, so if we look again at x equals 0 right here, what is it not? Well, in order to draw this, I have to pick up my stylus, move up here, and go again, which means we know that it's not continuous at x equals 0. Therefore, it cannot be differentiable there either. That is going to be sort of the key. So what are you doing? You're, in terms of the section, you're learning about where scenarios exist where graphs are not going to be differentiable. So the first three are not about continuity. They're about being able to actually find the slope of a tangent line at that point, whereas the last one is about continuity and the definition. So those are your scenarios that you're going to sort of be analyzing. So let's do some example problems in the section that would be sort of about how to apply this. The directions here say, let's determine the differentiability of a graph of the values a, b, c, and d. If differentiability does not exist at any one point, explain why. Okay. So what we're going to do is basically we go through the graph, and it has already been stated, and it probably, by the way, on an exam situation, it probably won't be stated. You'll probably have to find it. We'll get to an example of that in a second. But for this purposes, now that you're just learning this, let's talk about them labeling three values of, let's say, some values of x, right? Oh, well, it's over here, right? So some values of x, basically, right here. So they're saying if you go up from those values, there is going to be a lack of differentiability occurring on your graph. What they're looking for is for you to identify why. Okay, so if you go to A, we go up from A, we see this scenario happening here. So if I was to draw this, I clearly do not need to pick up my stylus in order to draw it. So that means it's not about continuity. It has to be about one of the other three scenarios. So what do? You go back and you say, well, what does this graph look like? Well, it doesn't look like a sharp corner, right? It doesn't look like a sharp corner. It doesn't look like any type of necessarily vertical tangent, though I'll explain why it might in a second. But it clearly looks exactly like a cusp. So the reasoning for why this is not differentiable is that it's a cusp. Now you might have heard just mentioned, so technically you might look at this and say, well, you could draw a vertical tangent right here. So this is a variation of a vertical tangent, but it's a perfect example of a cusp. So just to be clear, we would say that this graph is not differentiable at A because of the presence of a cusp. What about B? So if we worked our way up from B, we get to this, it looks like a hole in the graph. So what do we know about when we're drawing this and we reach this point? Technically, since there's a hole in the graph, I must lift my stylus to keep drawing. If that's the case, then what is being blown up here? Continuity. So we would say not continuous. Okay, since it's not continuous at this point, we therefore know now that this is going to be not differentiable at the point B. So what about next? So if we go up from here, let's say, right? If we go up here, we got something weird. It doesn't look like anything's happening over here. But if you look closely, what has happened is the graph has gone perfectly vertical, which means if I was to draw a tangent at that point, that tangent would be vertical. So if I can draw a vertical tangent at a point, therefore the graph will not be differentiable at that point because you can't find the slope of a vertical line. Now note, this is the most uncommon value because it's not very often that a graph goes vertical. And if you think deeper about it, you'll probably right away be like, that's right. I was like, we've had a lot of horizontal things, but not many vertical. Last point, let's say we are at x equals d, the point D. If we go up, what's happening? It looks like, again, we're lacking continuity. I have to lift up my stylus in order to actually move on to the rest of the graph. So here, got to lift it up and start here, so not continuous. So basically all 4 of these points of values of x represent areas on the graph where it is not differentiable for various reasons. It's just about understanding why in these scenarios. Okay, so what if they don't give you the values and you're asked to find them yourself? It says for letter A, for number 1, it says find the values of x in the interval -5 to 7 at which the function is not continuous. Okay, so this is going back to continuity, old material, so we're not doing anything new here. Just note here, this is definitely, as it says, an interval. So when I give this interval, I'm giving it with parentheses, which means I am not including -5 and 7. So basically when I go through here, I'm only including everything in from -5 and I guess 7 someplace over here, who knows, right? Somewhere in from there. So be very wary of that. I've had students that would literally choose -5 as a point. That is not what we're looking for. We're looking for anything inside -5 and 7, not including those numbers. So any value of x that lacks continuity. So we're going to have x equals what? So if we start at -5 inside of it and keep on going, where's the first point where I have to pick up my stylus? It's at x equals -3. If I keep on going all the way through, I'm like, I'm good, and then I get to x equals what? I have to lift it up, 0. I can keep on going from there. Give me a sec. I can keep on going from there, and then all of a sudden I get to x equals 2. Now note, there is a point down here, but that doesn't matter. I still would have to lift up my stylus to label the point and come back again. I keep on going, and I go, okay, I'm here. Well, it doesn't look like I have to lift up anything. I just have to keep on going. And then all of a sudden I go, wait, I've hit this dashed line right here, which we all know is an asymptote. So in order to eventually pick up my pen and continue on this side, I have to break continuity. So I've reached my 4th and final continuity, or point of discontinuity is the technical term that you learned in the previous section. Okay? So the key question is here, which is the new material. It says find the values of x in the interval -5 to 7 in which the function is not differentiable. Okay, so what does that mean? So you need to think about this from the standpoint of what you learned. So what breaks differentiability? Corner, vertical tangent, cusp, discontinuity. So I claim we already know 4 values of x which are not differentiable. What are they? Hopefully right away here you're staring at these, because if it's not, we already know that it's not discontinuous, or if it's not continuous, it's not differentiable. So we already know that all of these are going to repeat. So the question is there anything else that you see on the graph that would be a point of differentiability that has nothing to do with continuity? That is what you want to stare at. So if you want to pause right now and find it, you can. Okay, so hopefully everybody is looking right here. Why? Because it looks like we have a perfect example of a cusp where we're coming in at curvatures on both sides and it's changing the slope direction. So therefore we also have break differentiability at 5. So what are we doing? We're doing x equals copying these guys, adding a 5 in, and then getting our answer to our problem. Okay, last problem, number 2. Just like we have in the past, we've dealt with piecewise functions. So again, what is a piecewise function? So this function exists, the function x cubed minus 1 exists for all values 0 and to the left, but not including 0. Whereas 3x minus 1 exists, the line 3x minus 1 exists from anywhere including 0 to the right. So what we've been doing is we've been doing limits without seeing the graph, which is extremely valuable and important for what you're going to do. But for what we want to be able to see this to do these problems of continuity and differentiability. So all we're going to do is graph this. So real quick, x cubed minus 1. So what kind of points are happening there? Well, if you put a negative 1 in here, you're going to get negative 1 cubed, which is negative 1, minus 1 is negative 2. So let's say we go by, here, 1 second, let's do by boxes. 1, 2, we'll do 1 unit for 2 boxes on this axis. And then let's do just 1 unit for 1 box on this axis. Okay, remember, one of the things when you're handing in graphs and such, make sure everything has a scale, because scales are extremely important for this. So negative 1, negative 2 was the first point that we found, right? So we got that. What if we put negative 2 in there? We would get negative 8 minus 1, which is negative 9. So that kind of is not so good. That's way off our graph. So let's, that would be like down here somewhere. We'll estimate, right? And then at 0, if we do 0, we're going to get negative 1 as our value. So, but remember that, to be clear, that's not a filled in circle, that's an empty circle because we have a strictly less than. So if we just graph this real quick, we just need an estimate of what the graph looks like. It would look like that. So what else do we got? So for 3x minus 1, let's put in some points. At 0, we get, oh, look at that, we get negative 1. Okay. So what happens then? Well, that means that this actually fills in. So the empty circle fills in because it's actually happening, a value is happening at that point. If we continue on, if we do 1 into the graph, we get 1, 1. 1, 2, sorry, 1, 2. If we do 2, we get 6, we get minus 1, which is 5, so we're going to get 2, 5, which is there. And we know that this is going to be a line, so we do that. Okay. All right, so this is essentially our piecewise function. And we can now answer our questions. It says, does this function appear continuous at x equals 0? Well, if you look at this, if we travel along the graph, right, do we ever actually have to pick up our pencil? We don't, because the one graph filled in where the other graph wasn't. So therefore, we just keep on going. So yes, it does appear continuous. The question is, though, does it appear differentiable at that point? Well, continuity isn't breaking it, so is anything else breaking it? So again, hopefully most students will look at this and go, oh, well, if I did something like, if I blew this up and I went, if I go like this, like that, which is what's happening at the point 0, negative 1 right there, what is that? Well, it looks like sort of a cross between a cusp and a corner, so I would expect either one, which means no, it's not differentiable at that point. So, and this is the reasoning right here. So again, it's all about this section. It's very brief. I'm already done here. It's very brief. It's just about finding when points are not differentiable. Do not forget about this section. I find that students do very well on the other stuff, which is the hardcore calc, but they'll forget about this section and then get a really easy problem wrong, because I think most students, when they're done with this, are going to be like, wow, that was really super simple.